Does the universe spin? Exploring a new rotating cosmic model, we observe rotation everywhere. The Earth spins, the solar system revolves, and the Milky Way rotates. Given that everything in the cosmos seems to be in motion, it naturally leads one to wonder, does the universe itself spin? As early as the 1950s, mathematician Gödel, by solving Einstein's field equations, proposed a rotating universe model known as the Gödel universe. This hypothetical universe possessed some highly peculiar properties, most notably the existence of a spacetime structure called closed time-like curves. For those familiar with the grandfather paradox, a closed time-like curve is a special world line in spacetime where, if you travel along this closed path, the time dimension forms a loop, allowing you to return to a point in your own past, essentially time travel. However, the Gödel universe was purely a hypothetical model with many inconsistencies. For instance, its cosmological constant was negative, and the universe was static, neither expanding nor contracting. This contradicts our current observations of an acceleratingly expanding universe. A slowly rotating dark fluid universe, a new hypothesis. Fast forward to March 2025, a paper published in the monthly notices of the Royal Astronomical Society drew inspiration from Gödel's work. Researchers proposed a completely new model of a rotating universe, a slowly rotating dark fluid universe. Unlike Gödel's purely spacetime structure, this new model posits that our universe is a spherically symmetric ideal fluid. As it rotates, it causes spacetime to twist, creating a phenomenon similar to the frame-dragging effect observed near rotating black holes. This model could perfectly explain why the Hubble constant, as measured by the Hubble and Webb telescopes, consistently deviates from the value derived from the cosmic microwave background CMB. This is famously known as the Hubble tension. Specifically, the researchers introduced a global angular velocity of rotation to modify the gravitational potential within the Euler-Poisson equation under a Newtonian gravity framework. This modification influences the process of cosmic expansion, particularly the late-time Hubble constant. While the Hubble constant derived from the CMB aligns better with standard cosmological model predictions, it reflects the universe's early expansion. As time progresses and the universe enters its later stages, the additional expansion caused by rotation gradually accumulates, ultimately causing the Hubble constant to diverge from the standard cosmological model's predictions. The researchers suggest this might be the origin of the Hubble tension, the challenge of cosmic rotation and the evil axis. However, introducing cosmic rotation presents a problem. If the universe is so vast and truly spinning, wouldn't matter at its edges easily exceed the speed of light. To prevent the tangential velocity at the boundary of the observable universe from surpassing the speed of light, the researchers calculated an upper limit for the universe's current angular velocity, 0.00 rotations per billion years. This translates to one full rotation taking 500 billion years. Here's the crucial part. When the universe rotates at this maximum angular velocity, the Hubble constant aligns with the value observed via supernovae. Conversely, when the angular velocity is zero, meaning the universe isn't rotating, the Hubble constant perfectly matches the value obtained from background radiation, essentially reverting to the standard cosmological model. Could the Hubble tension truly be caused by cosmic rotation? Is our universe really spinning slowly? While the results are quite amazing, the model itself remains too rudimentary. Firstly, it's not a realistic model, but a simplified fine-tuning model, or perhaps a weak or toy model. It only employs classical fluid dynamics, not relativity, let alone quantum mechanics. Furthermore, direct observational confirmation of a rotating universe is extremely difficult. After all, it takes 500 billion years for one rotation, and the universe has only existed for 13.8 billion years. Human timescales are negligible in comparison. Indirect evidence. Galactic rotation and CMB anisotropies. Are there indirect ways to test this? Possibly. One approach could be by observing galaxy rotation. When galaxies initially form, the matter composing them is influenced by the overall angular momentum. If the universe itself is rotating, then the rotation directions of galaxies within the universe should exhibit some preference. While most current observational evidence indicates that galaxy rotation directions are completely random, there are exceptions. For instance, shortly before the aforementioned paper was published, Another article in the monthly notices of the Royal Astronomical Society reported that researchers, using Webb's deep field data, found 50% more galaxies rotating in the opposite direction to the Milky Way than in the same direction. According to the cosmological principle, the universe is homogeneous and isotropic. Homogeneity is straightforward. Matter is evenly distributed on large scales, meaning there are no significant regions with vastly more matter than others. Here, large scale refers to cosmic scales, far beyond galaxies or galaxy clusters, typically meaning at least 1% of the observable universe, or about a billion light-years. Isotropy, on the other hand, means that matter appears the same regardless of the angle from which you observe it. For example, a wheat field is isotropic. No matter which way you look, it appears similar. However, a sunflower field is anisotropic. The view changes depending on whether you're facing or facing away from the sun. This is called an isotropy. If the universe were an anisotropic sunflower field, then galaxies would be individual sunflowers. Theoretically, galaxies in the universe should be randomly oriented, facing all directions. However, the Webb observations suggest they might not be entirely random, but rather preferentially rotating in a certain direction. This phenomenon has been observed in both the northern and southern celestial hemispheres, and the effect becomes more pronounced with increasing distance from Earth. Thus, researchers hypothesize that the universe might have been born with an inherent rotation, giving its constituent matter a primordial bias in rotational direction. Later, as cosmic chaos increased, this difference in rotational direction gradually diminished. While this explanation sounds plausible, it's not the only one. Other possibilities still exist. For example, rotation direction might affect galaxy luminosity. Counter-rotating galaxies could appear brighter due to Doppler effects, relativistic effects, or even some unknown physical mechanism, leading us to observe more of them. Additionally, the celestial area selected by the authors is quite limited, less than 0.2 degrees. Considering redshift, the span is only a few tens of millions of light-years, which is far from a large scale for the universe. At smaller scales, gravitational effects can indeed cause various peculiar phenomena. For example, as early as 2014, scientists found that quasars exhibited a directional preference, with their rotation axes often aligned with their host structures. Quasar disks tend to be distributed along cosmic filaments. However, this phenomenon is currently thought to be primarily due to quasars inheriting the angular momentum distribution of their host structures, meaning the formation of fibrous structures influenced the orientation of internal quasars. The evil axis of the universe, beyond galactic rotation directions, can we discern any clues from the cosmic microwave background CMB? After all, it's the universe's fundamental background noise. If the universe itself is rotating, this would surely manifest in the background radiation, perhaps causing a temperature difference between one side of the CMB and the other. However, the CMB is famously uniform and isotropic. After accounting for Earth's relative motion in the universe, temperature differences across the CMB are only about 1 part in 100,000. Of course, one could argue that this might be because the universe rotates too slowly, so its effect on the background radiation is masked by random fluctuations. Overall, whether it's galactic rotation directions or CMB anisotropy, the vast majority of current observational evidence still supports a non-rotating universe. The rotating universe model discussed today, while innovative, still lacks observational evidence. It's more of a targeted technical adjustment to address the Hubble tension. More importantly, introducing a global rotation is a rather radical assumption. It would inevitably have a series of impacts on current cosmological models, leading to numerous inconsistencies with observations. If this model can subsequently reconcile its contradictions with existing cosmological observations, it could become a powerful extension of the standard cosmological model. Conversely, if theoretical and observational contradictions persist, its applicability will be severely limited. The evil axis and the cosmic anomaly wait a moment. If the universe is rotating, doesn't that imply it should have an axis? And what if we just happen to be on it? In 2003, NASA's Wilkinson Microwave Anisotropy Probe WMAP released the first high-precision map of the cosmic microwave background. When scientists analyzed temperature fluctuations on the largest cosmic scales, they discovered that at a certain scale, The distribution of temperature fluctuations was not entirely random, but aligned along a mysterious axis, which scientists dubbed the evil axis of the universe. In 2013, the European Space Agency's Planck satellite released even higher precision background radiation data, and the evil axis persisted. While the evil axis is merely a symmetry axis on the cosmic sphere and doesn't necessarily imply it's the universe's central rotation axis, its existence seems to indicate that the universe is not entirely isotropic. Scientists have proposed various explanations since, but to date, the evil axis remains an unsolved mystery in cosmology. It might be an observational illusion, an error in data analysis, or perhaps a clue to new physics. But it's also possible that it hints at a truly rotating universe. What do you find most intriguing about the concept of a rotating universe, and how might we go about further investigating such a subtle cosmic motion?